In this video lesson, I create an STM32Cube IDE project and set it up with Git for source code management. Using a source code management system is step one for doing CI/CD. And even if you don't do CI/CD, you should be using source code management. So here is a brief outline of the lesson. I start with some background on STM32CubeIDE, like what are the major components and what kinds of software and files make it up. To be clear, this is not a tutorial on this IDE. I assume you know a little about STM32CubeIDE and ideally have used it at least a tiny bit. Then I create an IDE project and go through the mechanics of creating a local Git repo that will contain our IDE project. Next, I go through what could be viewed as a Git server, and it contains what is called a remote repo. This repo is the official storage place for the project and is how code is shared between developers as well as with Jenkins. After I create the remote repo, the final step is to push the contents of the IDE project local repo to the remote repo. By the way, I believe there is an STM32Cube IDE plugin for Git, allowing you to do Git operations from the IDE GUI. I didn't go that route for a couple reasons. First, I think it's important to know Git at the command line, and this whole course is about moving away from the GUI and to the command line. Also, I have used GUIs that supported Git, and often I found myself just going back to the command line because I was more confident in what was going on. So to make it clear, here's a diagram of the project I showed in the introduction video. What we are doing in this lesson is in this dotted oval. So that is the IDE project, the local repo, and then the remote repo. So let's get started. Here is a diagram I created to illustrate the parts of the STM32CubeIDE. It's kind of busy, but it helps to understand a little bit how it works in order to use Git and to create automation scripts. So on the left side, we have the common parts of the IDE, and on the right side, we have an IDE project. So starting up here, we have what I call the IDE system. The first thing I show here is the Eclipse IDE base. This is a big piece that includes all of the common infrastructure for an IDE. The rest of the stuff is specific to STM32. First, we have a database of all the MCUs and boards that are supported. This database contains all the pinout and hardware information for those MCUs and boards. Then we have the pin and hardware configuration editor where we enable peripherals, assign pins, choose startup or choose software options and so forth. And we have the code generator, which generates code based on the project MCU and the hardware configuration. And finally, we have support for the ST-Link debugging interface. Next, we have IDE provided source libraries. First, there are libraries for interfacing to the hardware, like a UART or an I2C, and these are often called driver libraries. STM32 has two styles, one called HIL, one called LL or low level, and you often get to choose between them. There's another driver library called SEMSYS, which is more generic, not just ST, and it's supported by other suppliers. Then there are middleware libraries for things like RTOS or maybe a file system or a TCP/IP stack. The IDE copies these software libraries into your project as needed based on which ones you've chosen. Notice I've shown multiple copies of these source libraries. This is because different MCUs have different libraries. So when you create a project for a particular type of MCU, the IDE will download the correct version of these libraries. At the bottom here are the MCU toolchains. These are things like the compiler, the linker, and standard C libraries. The standard C libraries are for things like printf, math functions, and string functions. Typically, these libraries come with the toolchain as I show here. Now, just like the IDE provided libraries, there are different versions of the MCU toolchains for the different MCU types you might have in your projects. Now let's move to the right side. Here I show a project in light green, and of course there can be multiple projects. A project is contained within a particular workspace, and as I show, you can have multiple workspaces on your laptop. Both workspaces and projects have a top-level folder that holds the contents of that project or workspace. So let's look at the contents of a project. I first show the pin and hardware configuration settings. These are stored in a file with a .ioc suffix. I think IOC stands for IO configuration, but I'm not sure. Then we have the generated initialization code, the make files, the linker script. These are all generated files produced by the IDE system as shown here. And we have the IDE provided source libraries which are just copied in. We also have several properties or settings files that are managed by the IDE system. So when you change things using the properties window for your project, the changes are stored here. These settings can affect generated files like make files. The settings files generally start with a dot, so they are sometimes hidden in directory listings. Next, we have your files. The application code files are ones you've created yourself. The IDE has to be aware of these to include them in the build through makefiles. But otherwise, the IDE doesn't do much with these files. Of course, it allows you to edit them. Along with the application, I include build and test scripts. This is for the CI/CD pipeline, including things like the build script we'll be looking at later in this course. Following this are the build output files, including object files, map files, and the actual image files. As shown, they are created by the toolchain. So on the right here, I indicate which of these files need to be in source code management, meaning the Git repo. Now, it's pretty much everything except the build output files, which are not source code. And build output files can be regenerated whenever you want by doing a build, so you don't need to store them. At the end of this course, I'll discuss this topic a little bit more, and in particular, these properties files. Here I drill down a little more on the STM32CubeIDE project folder, in this case CI/CD class 1. You can see that this project folder is inside a workspace folder. Within that workspace folder, there is some metadata for the projects within it. I haven't really investigated too much what is in that metadata. Now we have in the projects folder a .settings folder, which contains project settings. Then we see two folders I created in red. One is for the code files I wrote, the app folder, and one is for CI/CD build tools. We'll be looking at these things in later lessons. So of the remaining folders and files, if you look at the ones where the text is black, that being core, drivers, middlewares, and these files, these are all generated or supplied by the IDE. So they are either code or project settings or files needed to do the build, like for instance this linker script down here. This leaves two remaining folders, the ones in green, and they are debug and release. These are where the debug and release builds are done. So these folders contain build output files like object code and images, but they also contain all of the make files that are generated by the IDE and used to do the builds. So regarding the Git repo, everything you see here goes into the repo with the exception of debug and release. In the debug folder, for example, the make files and a few other files needed for the build go into the repo, but not the build output files. And the same is true for the release folder. So now let's create the STM32CubeIDE project and the Git repo. Now this could be done fairly quickly, but I'm going to do it in smaller steps to provide a little more of a learning experience. So this is the plan. We create the IDE project, and as soon as we've done so, we immediately create a local Git repo and we commit the initial project files to that repo. After that, we construct the project in steps, for example, adding application code, and we commit the changes to our local Git repo as we go. So what this means is the Git repo will create a record of how the project was built up. And this isn't necessary, but I thought it might be useful. So finally, we create the remote repo and we push our local repo to the remote repo. So here are some suggestions and notes. First, I suggest you create your own IDE project and Git repo as described in this lesson, and not simply copy my repo from GitHub and try to import it. However, I did write some code and CI/CD scripts for this course, and you might want to use mine. Of course, you might want to use some of your stuff. It really depends on how you want to do this course and how much work you want to put into it. If you do want to use my code and my scripts, then my suggestion would be to clone my repo to some temporary location on your laptop and copy the application code, which is the app folder, and the CI/CD tools, which is the CI/CD tools folder, into your IDE project from that repo, that cloned repo. One other thing I'll mention, pretty obvious, you'll see a lot of path names in here. These path names have my login and so forth in them because they're just what I did on my on my laptop, so obviously those won't match what you're doing. And then finally, I mentioned a couple handy Git commands that we'll use in this lesson and that I use all the time when I'm working. And one is git status-u. It shows you a list of files that have been modified or created in your workspace. And so I use that as, I want to make sure that the files I modified are the ones I thought I modified, and it's usually to make sure I didn't modify something by accident. I don't want that to go into a commit, and also just see new files. The other very handy command is git diff. You can just see the differences between the files as they currently exist in your workspace and the previous version. You can also use git diff to do the differences between commits if you want to look back in history. I don't do that nearly as often. So let's get started. Step one is to create the STM32CubeIDE project. In my introductory course on STM32 Embedded, I go through this in detail, but here I just provide the basic steps. And the information here is specific to the work I did, like the particular board hardware. So then step two is to create our local Git repo. So I go to a Windows command window, I cd to the project folder and create the local Git repo. So here are the commands to do that. Here's the cd, git init creates a local repo. Now Git needs a username and email address, I think just for logging purposes. And normally you can have global settings for this and you don't have to enter them when you create a new repo. But in this case, I wanted to make them specific for this repo, and the reason is I have a special email address for this class, and we'll see this email address later. So we need to create the .gitignore file. It's an important file in Git, and so let me tell you about that. The gitignore file contains file name patterns, often using wildcards, that should not be stored in the repo. And this is why we're telling Git to ignore them. So in our project, ignored files are generally build output files, like the flash image file. We discussed these kind of files a few minutes ago. Ignored files will not show up as untracked files when running a command like git status-u, and that's what we want. We don't want to see them. So here is the gitignore file for this course. Now this file, the contents of it is based on experience because I know a lot of these, what the output files look like. Now if there is one in here I didn't know about, let's say I didn't know that star.su is a build output file. What would happen is I'd be working and I would do a git status-u and I'd see a bunch of these files as untracked, and I would say, oh, what are those? Should those be added to the repo? And I'd do some investigation and say, no, those are build outputs. I don't want them in the repo. And so I'd add them to the .gitignore so I wouldn't see them anymore. The other thing I want to show you, here's a special line. This exclamation point is sort of an exception to the rule. Generally, I don't want list files. Those are build output files. I found out the hard way, though, that the IDE creates a file called objects.list that is required to do a build, and so I had to put an exception to that rule, so it does, because it does get added to the repo. And then these files down here, test results, star.xml. If you happen to run HLI testing in your workspace, it will generate those files with the test results, and you don't want those in the repo. So going back, now that we have that created, the next step is to add all of these files to the repo. And we do a git add dot, and that means add all untracked files that are in the current directory or in subdirectories. And then finally we commit these files, means we're adding them to the repo. And when I do this on the command line, I usually put the comment of what the commit is all about on the command line as well. And so in this case, I just say we created the project. Here I am in a command window just after creating the IDE project. I want to quickly go through the Git commands so you can see them. If you want to take a closer look, you might need to pause the video because I'm going to go through it fairly quickly. So here's a directory of what it looks like just after we created it. The only change is I have already created the .gitignore file. So we can just look at that. There it is. So the first thing I need to do is create the repo, git init. Now I can do a git status -u, and it's showing a lot of untracked files. So the next thing I want to do is that git config to add my username and my email address, and I'm going to cut and paste those in so I don't make a mistake there in the typing. Okay, now again, that shouldn't have changed anything. Git status -u looks the same. Now we're ready to add the files to the repo. So git add dot. It's warning us about carriage return line feeds. This is the whole thing about carriage return line feeds between Linux and Windows. So now that we've added those, I can do another status -u. Now it says those are new files and they're ready to be committed. So we are going to do our commit, IDE create project. So it's just added them to the repo. Now we do a git status -u, and it says we're on the branch. There's nothing to commit, so we are now in sync. The files are in sync with the Git repo, the local one. Now we need to integrate our application code and the CI/CD scripts. I'll talk about the actual application in these scripts in later lessons, but we'll put them in the repo now. So we create the app and CI/CD tools folders, and we copy files into them. We need to add the code in the app folder and make it part of the project, so the IDE will build it. So to do that, we right-click on the app folder, and in resource configuration, we unexclude it from the build. Finally, we have to hook our application into main by modifying this file, course source main.c, which the IDE generated, and we add our function in there. So here's what we do in the while loop, the sort of the super loop. We declare the function and then we call it. So that's fairly straightforward. So once that is done, we want to add this work and commit it into the repo, the Git repo. So we do that as shown here. The next thing we do is we do a debug and release build to ensure that the code builds, it should, and that the make files and other build files are up to date. And then we want to commit that work. So again, we do a git add and a git commit. Here I am in the IDE, and I've already added the application folder and the CI/CD tools folder here. And I've also brought up main.c, and I can show you where I've added in the hook to the application. This is the generated file, and I'm calling the application code app_main, and I have the C file that contains underscore main. So this is the main application function. The last thing I want to do is make sure that the code under app is part of the build. So I right click on that, I go to resource configuration, exclude from build. They're both checked as if this folder is excluded from the build. I don't want that, so I deselect them, I say OK, and now that code will become part of the build. Here we are in a command window in the project top level folder. Let's see what has changed from a Git viewpoint. So first of all, there are a bunch of untracked files that Git is unaware of. These are the files we copied in the app folder and the CI/CD tools folder. We modified main.c to add that hook in, and then we also modified a settings file, and that was when we made the app folder part of the build. So we want to add these new files and the changes. So first we stage them. Now if I do a status-u, it shows it's staged some modifications and some new files. So now we want to commit those, and I'm going to cut and paste that command in. Okay. And now we can do a git status-u, and everything is up to date. So now I'm going to pause the recording and do the debug and release builds in the IDE. Well, the builds are done, so let's see what happened. And you can see again a bunch of untracked files, and these are all make files. So when I did that first build, it created all the make files. And we want to add all of these, so do a git add. And again, it's warning about the carriage return line feeds. That's sort of normal. And then I will, well, before I do the commit, I will do another git status. And now you can see all of the files are ready to be committed. By the way, a settings file changed. I don't know what exactly that was caused by, but it's fine. So now we can do a git commit. And there's that. And now we do a git status, and everything is up to date. So now everything is in our local repo, it's ready to go. So the next step is to push the contents of our local repo into the remote repo. But that remote repo doesn't exist yet, so we hold off on this step until we create the remote repo. So going back to this diagram again, we have created this repo, it's all ready to go, and we want to push it to the remote repo up here. And so this is what we're going to create, and this is needed because this is where Jenkins is going to get the code from. So let's create the remote repo. I put the word server here in quotes because it's like a server, but it's actually running on our laptop. So the remote repo is actually a bare Git repo. That's another term. And that's the normal method used to share code among users, including Jenkins. So here's some things about a bare repo. Normally it's used for the official copy of the code. For example, GitHub repos are bare. Normally it is remote, in contrast to the local repo where you do your work. In our case, we have a repo within the IDE project. It cannot directly be used for development to locally modify files. The way it normally works is you make your modifications in your local repo and then you push them into the bare repo. So our automated builds done by Jenkins obtain the code from this Git server of the bare repo. For simplicity, for this course, we use file URLs to access this server. Rather than SSH or HTTPS URLs you would normally see with Git. And we're able to do this since everything is on one laptop. We don't need a network. And I did this just to try to make it a little bit simpler. So to create our bare repo, it's pretty simple. We cd to the parent directory, and I created a folder called repos where I'm going to put all of my bare repos, of which there's now one. You make a directory for the bare repo, the name of the repo, and then by convention, this directory or folder has a .git suffix. we cd into there, and we run git init with the -bear option, and it's done. So the URL for this repo is here. It starts with file colon. It's basically the path. And so now that we have the bare repo created, we can go back and push the contents from our local repo. So I'm back in my Git project, and I can now push the local repo to the remote repo. For convenience, so we don't have to enter the URL of the remote repo all the time, we can give it a name and then use that name. So here is the command to define a repo and give it a name. So we say git remote. We want to add. We're going to give it the name origin, which is the conventional name, and then here is the URL. So now our local repo knows about that. Now we can push the code. Normally I just do a git push and that's all it's needed. But for the first time we have to tell it what the default remote repo is and the branch. So I just say we're going to push to the origin and we're using the master branch. And there it's working. And now everything has been pushed to the remote repo. Before leaving Git, I want to show you a few things. First, let's look at the history of our local repo using git log. So there you can see the 3 commits that we made. So now let's say we want to find the difference between 2 of those commits, but we want to start by just looking at the names of the files that changed. So there are a lot of ways to do that. I'm going to cut and paste in a diff command. In this case, we're identifying the commits by using these hashes, which are unique strings, but the command doesn't require you to give the whole hash. You can just give enough that it's a unique value. So we can do this. Is going to give us the difference between this commit, the first commit, and the second one. And there is the list of the files. And let's say now we want to see what happened to main.c. So I'm going to edit this command line by getting rid of -name only and adding core source main.c. And there you have it. It shows that we've added those lines at main, that if you'll remember. Also, it looks like I must have inserted some spaces, and this existing line it shows it as being removed and then re-added, lined up with these two. So source code management, it's a complex subject. This is just a tip of the iceberg, but I hope this gives you a feel of what's going on when you use source code management. You might remember that I use an STM32 Blue Pill board for my hardware-in-the-loop simulation hardware to monitor and control GPIO. So I created another IDE project as well as another Git repo for this board. The hardware-in-the-loop simulation hardware uses the same application code as the main project, and I'll discuss that application in a later lesson. But there are some IDE configuration differences. First, the IDE does not know about Blue Pill boards. It's not an ST board. So when you create the project, you just have to create one for an MCU of this type. Now this means that there is also less hardware configuration already done for you. You have to do more yourself. So first, you need to enable debug. This is critical because if you don't do this, you may have problems flashing the board in the future. You also need to configure the UART for the console serial port. Now, clock configuration can be modified to get a much faster clock, 72 megahertz, based on the 8 megahertz crystal. The default configuration gives you a very slow clock. So to do this, you first have to enable the crystal, and here's how you do that. Then you go to the clock configuration tab. Now it's difficult to sort of explain the exact changes, so here's just a screenshot with the changes highlighted in red. And you should then see, for example, these output frequencies. Here, by the way, is the 8 megahertz crystal that we enabled. There's a lot of good information on the web about using these boards, And here's a particular one. I actually used this website to help me with the clock setup. So I have just one prompt for this lesson, so let's go through it. Are there any downsides to creating the IDE project repo in several steps or commits as we did in this lesson? Besides creating this history, can you think of any other advantages? Well, the downside is the repo will be slightly larger because we did it in steps. If we would have just waited until the end, until we had everything set up, and then just did one commit, the repo would be smaller, not by much. Now, the advantage of this, or an additional advantage, is if you made a mistake halfway through, we could have backed out the last commit and got rid of the mistake and redid it. It would be cleaner, you would have removed the bad stuff, but on the other hand, this happens all the time in software. You're always making mistakes. And so normally people don't back out commits because sometimes there's complications in doing that. Normally people just fix the mistake and just do another commit. So here's a brief summary of the lesson. We looked at the contents of an STM32CubeIDE project to decide what parts would be stored in a Git repo. We created a Git repo for our IDE project and added to it in several steps. We created a remote repo, which is a bare repo, for official storage of our code and to share it with Jenkins. And finally, we pushed our local repo in the IDE to our remote repo. Well, this is the end of the lesson on setting up our Git repo and Git server. Thanks for watching.